Welcome. After learning about the basics of the equilibrium vapor-liquid separation, in this particular lecture, we shall be doing a few problems on the equilibrium vapor-liquid separation. And what we shall see, that we shall learn about the use of the relative volatility for estimation of the composition and the volatility of a vapor-liquid mixture in equilibrium and generate the vapor-liquid equilibrium composition diagram. Now, first we shall see this problem. This problem states that we have the relative volatility of a component A in a mixture of B, and we have given alpha AB as 2. This value shows that A is more volatile than B, that because it is this alpha AB is more than 1. The equilibrium ratio of B is Kb is given as 0.7, that means Kb is the equilibrium vaporization ratio or the volatility. The volatility of B is 0.7 and we have been asked to figure out the value of alpha BA. Now, these are the given values to us and we have to find out the value of the KBA, and also we can also find the value of the volatility of component A. Here we have the solution that alpha AB is defined as Ka by Kb, whereas alpha BA is Kb by Ka. That means alpha BA is reciprocal of alpha AB. So, here to get the value of alpha BA, I simply take the reciprocal, that is 1 by 2, and 1 by 2 gives 0.5. So, this is the relative volatility of B with respect to A. And here are finding the value of Ka. Ka is alpha AB into Kb. So, we just put these values, we find 2 into 0.7, that gives us 1.4. So, this shows that the component A is more volatile than component B, and in case of any kind of separation based on the vapor liquid equilibrium, we will find A will be going more into the vapor phase than B. B will stay more in the liquid phase, and that is how we can get separation between A and B. Next problem we take. In this problem, it is given that the relative volatility of A with respect to B is 1.5, and we have to find out the mole fraction of B in the first droplet of liquid condensed from an equimolar saturated vapor mixture of A and B. So, we have a mixture, vapor mixture, that is saturated of A and B, and the first droplet of liquid will be formed from this thing, and because it is saturated, we are assuming that A and B are in equilibrium. So, we have to figure out that what is the composition of the first liquid droplet formed from this particular vapor. So, in this case, what we do, we go by this thing that alpha AB is 1.5 and the vapor mixture is equimolar. Equimolar means the mole fraction of A is equal to mole fraction of B, and because the summation of the mole fractions is always 1, so we divide 1 by 2 and we get the mole fractions of A and B as 0.5. And what we have to find out? We have to find out the mole fraction of B in the liquid phase. For solution of this problem, we go to the basic definition of the relative volatility, which is given by alpha AB as Ya by Xa divided by Yb by Xb. Here what we do that, and this is given as 0.5. So, we find that this Ya and Yb being same, so we can cancel these things 2 out and we get Xb by Xa equal to 0.5, and because Xa plus Xb is unity, then what we get 1.5 Xa. That means we are substituting for Xb 1.5 Xa plus Xb will be equal to 2.5. 2.5 Xa is equal to 1, and Xa value is coming out to be 0.4, and then we get Xb as 0.6. There is a small mistake here. It will be 1.5 Xa Xb plus Xb, that is 2.5 Xb. So, instead of Xa, please read it as Xb. So, this will be Xb and this is xb and this is xa. Now, this you can also check internally because the alpha value is 1.5, so xa has to be more than xb. So we are finding this. This is the thing. Am I right? Yeah. Hello. আচ্ছা আমি না এই প্রবলেমটা রিপিট করতে চাই। হ্যাঁ এই প্রবলেমটা শুধু রিপিট করতে চাই। হ্যাঁ it was correct. कभी ना you never write 1.5 xa equal to xb, you write xb equal to 1.5 xa. শুধু এই প্রবলেমটা। হ্যাঁ এক মিনিট আমি যাই প্রবলেমটা এ কি হলো। হ্যাঁ now we have the next problem. In this problem what we are given that there are again two mixtures of A and B and the relative volatility of this is given as alpha AB as 1.5 and we have to figure out the mole fraction of B which will be the when it is this particular mixture A and B if it is in saturated vapor phase gets frozen and gets condensed and forms the liquid. So we have to find the mole fraction of B in the first droplet when this saturated vapor of A and B is condensed. Now please understand this that because it is saturated vapor, a slight decrease in the temperature will cause the condensation and that what is called the dew point temperature at the given pressure, and we have to figure out that when this first droplet is condensed, naturally the droplet will be having more amount of the less volatile component, and from the given data we find that the A is more volatile than B. So the liquid droplet which will be formed will be having more of B than A. So this physical understanding, this physical picture should also be reflected in our solution. So let us go to solution. We find that alpha AB is given at 1.5 and because it is a equimolar mixture of A and B in the vapor phase, so we find that the mole fractions of A and B will be is equal to 0.5 because the summation of the mole fractions is always unity, and we have to figure out the value of the mole fraction of B in the liquid phase. Now for the solution what we do, we go to the definition of alpha AB, and here we find that YA by XA divided by YB by XB and is equal to 1.5 because YA is equal to YB. So we can cancel out YA and YB and we are left with XB by XA. That means XB equal to 1.5 XA. Now because XA plus XB is equal to 1, what we do, we substitute for XB from as 1.5 XA and we get 2.5 XA, and this gives us XA equal to 1 by 2.5 as 0.4 and we find XB equal to 0.6, and this says that because as we said earlier that because B is less volatile, so it has more tendency to go to the liquid phase, and that is how we also find that our solution shows that the mole fraction of B in the liquid phase is more than that of A. This gives some internal check for you during the solution of the problem. Next problem we attempt is a mixture of A, B and C at these mole fractions 40 mole percent of A, 40 mole percent of B and 20 mole percent of C. To check that whether these values are correct or not, you can simply add these values and check that whether they are coming to 100. Since in this case it is coming to 100, that means our given data is fine, and if it is not coming to 100, then we have to say that something wrong with the data or maybe we are missing some other component. The solution can be taken to be ideal, and with this ideal assumption these are the relative volatilities alpha AB and alpha CB which are given. Alpha AB, that means 2.4, that means A is more volatile than B, and alpha CB is 0.43, it means C is less volatile than B. So, overall picture is that A is more volatile than B and is also more volatile than C. So, A is the most volatile component, whereas C is the least volatile component in the particular mixture. And here we have to figure the value, that value of alpha Ca. Now, by physical understanding we see that alpha Ca must be less than 1. So, this also we should find out from our solution. So, here is solution, that we write alpha AB equal to 2.4, alpha CB 0.43, and to get the value of alpha Ca, what we do, we write the basic definition, alpha AB equal to Ka by Kb, alpha Cb is Kc by Kb, and alpha Ca is Kc by K. So, to get Kc by K, what we do, we divide both the numerator and the denominator by Kb, and this Kc by Kb is nothing but alpha Cb, and K by Kb is nothing but alpha Ab. So, we put these values of this alpha Cb and alpha Ab and get these values as 0.18. So, as we said that this value of alpha Ca as 0.18 tells us that the C is less volatile than A, and if we compare these three values, we find this is the least value between Cb and Ca, this is lower. So, it tells us that C component C is the least volatile of the three components. After learning about this calculation of the relative volatility, what we now go, that we have to go for a problem as we discussed earlier, to know that what is the state of the mixture. Now, we learnt it that when we want to carry out some flash, we need a two-phase system, not a single-phase system. That is, we want a vapor-liquid mixture and not just a subcooled liquid or a superheated vapor. So, for this, before we go for the flash calculation, we need to make sure that we have a two-phase mixture. So, here is the problem to know that whether we have a two-phase mixture or subcooled liquid or superheated vapor. So, here again we have a mixture of A, B and C, and these are the respective mole fractions. Here mole fraction of A is 20, mole percent of A is 20, mole percent of B is 40, and we can now deduce the mole percentage of C by subtracting this 20 plus 40 from 100. That means this 60, that means C is 40 mole percent, and here we are given the equilibrium ratio as 2.25 for K1, K2 is 1.02 and K3 as 0.6. And as we learnt earlier that because here some of the K's are more than 1, some of the K's are less than 1. So, it is not directly possible for us to ascertain what is the state of the particular mixture. So, what we do, that we take this thing, that we find the, put the I, this table we make, in this I the component name 1, 2, 3, and then we put these components are nothing but A, B, C, and then we have the Ki values at 2.25, 1.02 and 0.6, and X or Y. I will say what is X or Y because this percentage given may be taken either to be the liquid phase composition or to be the vapor phase composition, because initially we do not know that whether this particular mixture is residing in the vapor phase or in liquid phase or in both the phases. So, we say that this is Xi or Yi, and then what we do, we simply multiply this Ki with these values, and we get Ki Xi in this and Yi by Ki as this. So, we multiply and divide this kind of things to get these values of Ki Xi and Yi by Ki, and then sum them up. So, after summing them up, what we do, that we refer to this particular logic, that summation Ki Xi is more than 1 and summation Yi by Ki is also more than 1. And when we refer to this particular table, we find that this particular condition, that is summation Ki Xi more than 1 and summation Yi by Ki more than 1, gives us a mixture of vapor and liquid. That means, for the given condition in the system, we have a system which is more than its bubble point, but less than the dew point. Okay? So, that means that we have a two-phase mixture which is there between the dew point and bubble point. Now, next problem statement comes like this. Here we are trying to use the knowledge of the relative volatility to generate the composition diagram of a vapor liquid equilibrium system. Here we are given a binary system A and B, which is taken to be ideal, and we have to draw the xy, that is the x is the mole fraction in the liquid and y is the mole fraction in the vapor, and for the given value of the relative volatility, in this case we find that it is 0.47. It means the A is less volatile than B. So, what we now do, that alpha is given as 0.47, we have to plot x and y, and we go with this particular equation in which we find that y by x is taken to be that of A, and 1 minus x and 1 minus y are the liquid phase and vapor phase compositions of B. So, here we simply rearrange the equation and we get this particular equation y in terms of x. Now, once we get this, now by putting the value of alpha, and for different value of x, like we can put from 0.0, 0.1, 0.2, and we know that the mole fractions will always be between 0 and 1. 0 is when x is 0, it means it is pure B. When x is 1, it will be pure A. So, between 0 and 1 this will lie, and we get this value of x, put the value of x here, and alpha is constant for all of them, and for each of these pairs we can find the value of y. And this is how we can now plot these x and y values, and for this plotting you can use any kind of software. Here we have shown a snapshot which has been done with Excel. So, you can use any software to generate this kind of plots. So, here we find that this is the on the x axis we make the x, and on y axis we make the y, and here you can see that scales are from 0, 0.1, 0.2 etc., and similarly 0.1, 0.2 etc. on the y axis, and we find that this is the nature of the curve. Now, please note that this, it may be concave or convex upward. In this case we find it is concave upward. Now, whenever you have the curve which is made for the low volatile component, you will always get a concave upward. And if instead of A, suppose you are plotting B, what you will find? You will find a plot like this, that will be concave downward. So, when you are drawing these curves, if your logic is right, then looking at the curve generated, you should be able to decide that whether you have plotted this thing rightly or not. Since this is concave upward, so it is clear that we have calculated the values of x and y correctly. After this problem, we shall be now going to a problem on the flash separation. So, here we have the problem. Here we have 4 components, propane, butane, pentane and hexane, identified by some tags 1, 2, 3 and 4 with this composition in terms of the mole percentage, like this is Z1, Z2, Z3, Z4, and this is the flow rate of the feed, and this is given at this particular pressure and this particular temperature, and we have been asked to determine the fraction of the feed converted to vapor and the composition of the product liquid and vapor assuming equilibrium. So, we need the equilibrium data, and these are the values of the equilibrium constants for the 4 components. So, what we do for solution? First we write out the information which we have been provided with, and then these x and y represent the compositions of the product liquid and the product vapor. Here we are going to use these 2 equations which we derived earlier to find out the flash problem and the vapor composition and liquid composition after the flash, and this is the equation which we shall be solving to get the value of the vapor fraction, that is psi, and the k value have been given to us, and we shall be using the Newton's method, and in this Newton's method this is the recurrence formula to update the value of the root. In this case, this is psi is the root which we have to find out. So, before we go for the solution, we have to first ensure that the given values are for 2-phase mixture. So, for that what we do, as we learnt earlier, we first put the value of psi as 0 and find the value of f psi, and then we put the value of psi as 1 and find the value of f1, and we find from these values of f0 and f1 that this is a two-phase mixture. Now, after making sure that this is a two-phase mixture, we go for the solution, and here the solution is that because we know that psi is going to lie between 0 and 1. So, to start our iteration, we assume a value of 0.5, and we know that the Newton's method works very well if we have a good initial guess. So, here we are bound by the value of psi, so we are taking it as 0.5, and with this 0.5 we do the iteration, and we find that the value of this f psi and the f prime psi with this psi, and we update the value of the psi to psi k plus 1, and then we find the percentage deviation, and then we go using this latest psi, again we find the value of f psi and f prime psi to update the value of psi, and we find the percentage deviation between the two consecutive roots, and we find that the deviation is coming down, and we continue this thing here, and we find that slowly and slowly the percentage deviation is coming down, and ultimately it goes to a very acceptable limit. So, what we do, we take this value of psi as our root. After finding the value of psi, and what we do, we take these equations, these two equations, put the value of psi here and incorporate the values of the Ki to get the compositions of the liquid and the vapor in terms of the mole fractions of each of the components, and here we find in this table we find the value of xi and yi for each of the components. To check whether our solution is right or not, what we do, we sum up the xi values and sum up the yi values, and we find that their sum is coming to 1. So, this gives us an internal check about the validity of our solution. So, with this we are able to solve this flash problem, and we find the fraction vaporized is 0.12 something, and then we have the compositions. So, these are the books which you can refer to for more detail. Thank you.